the cross product. And cross product is something special to 3 dimensions. So we didn't talk about cross product with vectors in 2 dimensions. We'll go ahead and begin with a little bit of information about the cross product. So the cross product is a vector that is orthogonal to 2 given vectors. And this can only happen in 3 dimensions. So I'll draw a picture of what that looks like here in just a moment. What's up?
It's last Friday.
Last Friday, last day now. It's crazy. The year is almost over. I can't believe it.
This time?
Yeah.
Would that just be like the axes since they're orthogonal to each other?
Yes, it's like that. Okay. It wouldn't have to be, like if you're thinking about the XY plane, it wouldn't have to be that those 2 are orthogonal to each other. They are, right? The x-axis and the y-axis form a right angle. They could form any such angle. So really we're talking about 2 vectors. So I'll draw a picture here. Here's 2 vectors. And they would be, like any 2 vectors, you could always find a plane that they share. Okay, so wherever they are in space, there's a plane that intersects both vectors. Okay. The cross product is the vector that's orthogonal to both of those. Okay, so there are 2 right angles formed, one with this and then one with this. So can you kind of picture that in space? Okay. And it's very similar to like the z-axis, okay, because we're drawing that perpendicular. But then again, the 2 vectors that it is orthogonal to don't necessarily have to be orthogonal to each other. So we could imagine like maybe there's a 30-degree angle between those 2 vectors, but it's still cross product. Okay. So here is some statement we're going to use the standard unit vector notation for u and v. So we're going to let u be u sub 1i plus u sub 2j plus u sub 3k. And v will be v sub 1i, v sub 2j, v sub 3k. In component form, you could think about those vectors like u sub 1, u sub 2, u sub 3. And v would be v sub 1, v sub 2, v sub 3. Then their cross product is, note that it's notated with like an X in between them as opposed to a dot. So we're talking differently than the dot product. We're talking about the cross product. You're going to see the X cross in between the 2. Do you remember in what unit we saw these?
Unit before.
Well, not necessarily the number, but the topic, matrices. Do you remember what this is called when you don't have the matrix brackets, when you have the straight lines? What are you finding? The determinant. Okay. So the cross product is the determinant of a 3x3 matrix. The cross product is going to be another vector. It's going to be another vector in standard unit vector notation. So it's going to look like these, where it has I, J's, and K's, and we're adding different pieces. And how will we get what that new vector is? We'll do this 3x3 determinant. Okay, so we'll see that on the next slide. We'll do some examples. Note that the first row of the matrix should be IJK for the cross product. So top row is IJK, and then you can put in U, the first vector in the second row, and V, the second vector for the product in the third row. So let's look at an example. This is from yesterday. How about this? Got to delete a slide. Let U be I minus 3j plus 2k. And V is 2i minus j plus 2k. we're going to do the cross product of U and V. On the test next Wednesday, you'll have to pay careful attention. Is it asking you to do a dot product or a cross product? Okay, so what's in between the U and the V will matter. I'm going to set up my determinant for my 3x3 matrix. And so my first row is always going to be IJK. For the second row, I'll use only the coefficients from U. So the like U sub 1, U sub 2, U sub 3 values. That would be 1, -3, 2. And then for the third row, I'll use the V sub 1, V sub 2, V sub 3, so 2, -1, 2. And then as a quick refresher for calculating 3x3 matrices, it's the easiest way to do it is to copy the first two columns because you're like multiplying on the diagonals and you'd have to like wrap around your matrix. We talked about that back in, I think it was chapter 8. But in order to avoid having that wraparound issue, I just copy my first two columns. And then you multiply the diagonals. You always start with the diagonals coming down from the top left. Okay, so I times -3 times 2 is -6i. J times 2 times 2 is plus 4j. And k times 1 times -1 is minus k. And normally in matrices, we would have had just numbers. We would have added them up and got a single number. We have things that have ij's and k's, so we can't combine them because they're not like terms. But then we have to do the three diagonals going up from the bottom left. Remember that you're subtracting those diagonals. So 2 times -3 times k is -6k. -1 times 2 times I is -2i. And 2 times I times j is 2j. And then you're really doing like adding the opposite of those second diagonals that you found. So always remember to distribute the negative to all three of those things. And you can now combine the like terms, i's with other i's, j's with other j's, k's with other k's, and that's going to be your final cross product. Okay, so this is really going to be plus 6k plus 2i minus 2j. So -6i plus 2i is -4i. 4j minus 2j is 2j. And -k plus 6k is 5k. So I have a new vector in standard unit vector notation with I, j, and k. But it should only have 3 terms. Let me finish. Are we okay with that? Does anybody have any questions? I would like you to do 2 on your own, just kind of practice running through the process. The next one I want you to do is V's cross product with U. So that means when you set up your cross product, what are you going to change? The second and the third rows, right? They're going to flip-flop. Okay, so see what happens if you do cross product of V and U. And then I'll also have you do one where you do a cross product with itself. So the cross product of V and V. So set those up. If you're having trouble setting them up, let me know. For B, the cross product of V and U, just read me your final vector there. 4i minus 2j minus 5k. Okay, that is the correct answer. What kind of connection do you see to the cross product going the other direction? Lucy?
It's like the same, but it's just different.
Change of signs, right? So on the next slide, that's one of the properties. If you do the cross product of v and u, and then you do u and v, they're going to have the same numbers, but they're going to be opposite signs. So one is just the opposite of the other. Okay, so they're not exactly the same, they should be opposites. What did you get when you did the cross product of v and b? 0. So if you do the cross product of a vector with itself, you'll always get 0. That's another thing that we're going to talk about on the next screen. So on the next screen, these are algebraic properties of cross product. You do not have to write them down. Okay? The two that we just illustrated, if you want to write down, okay, they're just kind of interesting, and we just saw this happen. A cross product of a vector with itself is 0, and then the cross product of u and v is the opposite of the cross product of v and u in that direction. Okay, so those would be two properties that maybe I would include in my note. You can see these other properties. Let me check what page number they are on the textbook. These are on page 789. Okay, so if you want to write page 789 in your notebook, just so that you're aware, there are some other algebraic properties, and you can look those up. Okay. There are also some geometric properties of cross products. Okay, and the geometric properties of cross products, I'm going to go through them. You don't have to write all of these down. These are on page 790. So if you do want to go back and look up, you can look up page 790. There's one in particular that we're going to address here. The cross product of u and v is orthogonal to both u and v. That's part of the definition, so when we drew that picture. The magnitude of the cross product is equal to the magnitude of u times the magnitude of v times the sine of theta. Okay. The cross product is 0 if and only if u and v are scalar multiples of each other. So if they differ by a scalar, you'll also get a cross product of 0. Okay. And the magnitude of u and v is the area of a parallelogram having adjacent sides u and v. So this is actually the one that we're going to talk about next. So if you want to put one geometric property in your notes, it would be this one. The magnitude of the cross product for u and v is equal to the area of a parallelogram that has u and v as adjacent sides. So our next example is going to illustrate this. We're going to be talking about a parallelogram, so it's going to feel like a little road trip back to geometry. Okay, so we'll draw out a parallelogram and look to see, is this in fact a parallelogram? And then we'll be able to find its area. Okay. And its area will just be the cross product. Or sorry, not the cross product, but the magnitude of the cross product. Okay, so here's our example. Show that the quadrilateral with the following vertices is a parallelogram. So this can be our number one job. We have to prove that we have two pairs of opposite parallel sides. Okay. And then if we can prove that it's a parallelogram, which we are going to do, then find the area of the parallelogram. Okay, so we're doing really like two different tasks here. Showing it's a parallelogram, and then once we do that, we can find the area of the parallelogram. So I'll give you a minute to write that down. Okay, I'm going to start by drawing an image of a parallelogram. Okay, so remember parallelogram, something like this. And I'm going to label the vertices of the parallelogram A, B, C, D. So generally in geometry, when we name figures, most of the time we name them in alphabetical order. So I'll just kind of assume that that is the case. Okay, A, B, C, D, one way or another. And then that allows me, and I'm not even plotting those specific points, right? That would be oriented in some manner on the coordinate plane. I'm not even worried about where those points are, because what I want to do to prove that this is in fact a parallelogram, I want to show that I have two pairs of opposite parallel sides. Right, that's the definition of a parallelogram. And so then I'm going to pull on my knowledge from yesterday in three-dimensional vectors. I can prove two vectors are parallel if they're related by some scalar. Okay, so we talked about that yesterday. So what I'm going to do is I'm going to find the vector for each side. And then I should hopefully see that there are two pairs of parallel sides. So by drawing out the parallelogram, I'm a visual person, it helps me say like, okay, one of the vectors I need to find is AB in component form. When I do AB in component form, I do my terminal minus initial. So 3 minus 4 is negative 1. 4 minus 3 is 1, and 2 minus 0 is 2. I'm also going to check BC. I'm going to leave a little space under my AB because if BC is adjacent, it's not going to be the one that's parallel. So I'm going to leave a little space so I can do CD underneath AB, so I can better look for my scalar. Okay, so I'm going to do BC. I'm going to do terminal minus initial. So 3 minus 3 is 0. 2 minus 4 is negative 2. And 6 minus 2 is 4. So those are two adjacent sides. Now, in order for this to be a parallelogram, AB must be parallel to CD. Okay? So then I'm going to do CD. And I'm doing terminal minus initial. So 4 minus 3 is 1. 1 minus 2 is negative 1. And 4 minus 6 is negative 2. When I look at those two vectors, is there some scalar that relates them? What would the scalar be? Negative 1. Yeah, you're just multiplying 1 by negative 1. So we could say something like AB is equal to negative 1 times CD. So they are parallel because they have a scalar. The same thing should happen for BC and DA. Okay, so I have one more side to find. I'm going to do DA. And in the order that I'm doing it, I'm just going around, clockwise here. So now my terminal point is A, and my initial point is D. So 4 minus 4 is 0. 3 minus 1 is 2. And 0 minus 4 is negative 4. when I compare these two, are they parallel? Yeah, by the same scale or -1. So we can say something like BC is equal to -1 times DA. It could also be flip-flopped, okay? Wouldn't matter which order you wrote them. Have we proven that this is in fact a parallelogram? Yeah, so that's pretty easy, right? Okay, you just go around all the sides and make sure that you have two pairs of opposite sides that are parallel. Okay, and if you have the drawing, it makes it easier for you to see which sides are opposite. Okay, so now that we have the fact that it is in fact a parallelogram, okay, it is a parallelogram. That's my geometry definition for parallelogram. Then we want to find the area of the parallelogram. So this is going back to that geometric definition. Okay. And I'm going to flip back to my previous slide. The area or the magnitude of the cross product is the area of the parallelogram that has U and V as adjacent sides. So in order for you to find the area of the parallelogram, you need to go back to your picture and you need to pick two adjacent sides. What sides do you guys want to use? I'll choose AB. What other side do you want to pick that's adjacent?
80.
80. Okay, these two sides are adjacent to each other, so let's find the cross product. We already have, we're going to use AB and DA. We already have the vectors, so we just need to put it into cross product. Let's see, I'm going to do AB's cross product with DA. And I set up my 3x3 determinant. IJK in the top row, AB in the second row, and DA in the third row. It would not matter if you chose a different pair of adjacent sides. Maybe you chose AB and BC, or you choose BC and CD. We're all going to come up with the same area as long as we choose adjacent sides. So copy your columns. Always do the diagonals down first. -4i plus 0j minus 2k. Subtract the diagonals going up. 0k over here. 4i, 4j. I am subtracting all of these things, so you could do add the opposite. If you want, you can do plus, and 0 doesn't have positive or negative, but we can make both of these -4i and -4j. That helps you. So we would come up with -8i minus 4j minus 2k. Can anybody verify Miss Conti did her math correctly? Okay, good. Now, that's a vector, right? That's not an area. So the area of the parallelogram, and remember, is the magnitude of the cross product. So I'm going to do the magnitude of my cross product. Right. And you've already done your cross product, so you just have to do the magnitude. Magnitude is the square root of all of the components squared and added together. So it would be -8 squared plus -4 squared plus negative 2 squared. And that'd be 64 plus 16 plus 4. It gets me to 70, 80, square root of 84. Which I can reduce, 4 goes into 84 21 times. So that would be 2 square root 21 units squared. So that's the steps you might take. There'll be some questions on your homework. And again, like really chunk it up into the special things that you're doing. If it asks you first to prove it's a parallelogram, just draw out a parallelogram and find all the vectors, and you should see scalars. Okay, showing you that the lines are parallel. If you have pairs of opposite sides, then you can do the cross product. Doesn't take long. And then find the magnitude of that cross product. If you found that it wasn't a parallelogram, you would not be able to find the area. We don't have the area formula for other quadrilaterals. Okay, there is one more piece of information that we have to talk about today, and that is called the triple scalar product. Triple scalar product is going to use 3 vectors. U is equal to u sub 1i plus u sub 2j plus u sub 3k. V is v sub 1i plus v sub 2j plus v sub 3k. And W is w sub 1i plus w sub 2k, or j plus w sub 3k. So you have 3 vectors. And the triple scalar product is a dot product with a cross product. So it's represented as U dot V cross W. Now, one way to find the triple scale product would be to do them individually. Find the cross product of V and W, you'll get a new vector, and then you would have to do a dot product with 2 vectors. This is a simplified method of finding it. Instead of having to do 2 separate operations, basically do one 3x3 determinant with all 3, and that's going to be the same thing as the dot product with a cross product. And so it's kind of like eliminating out a middle step. It's been simplified. So your first one, your outside vector will go on top, and then the 2 cross products should be in rows 2 and 3. Okay, so just go in order. So we could find this triple scale product. Note that if you're doing a cross product, your answer is another vector, because that is the vector that's orthogonal to your other 2. So it has an I, J, and K in it. When you do a triple scalar product, your answer is a number, because it's a dot product. And the answer to a dot product is a number, not a vector. That's always been true since chapter 6. I just got to set up my 3x3 determinant. U, V, W. And perform a 3x3 determinant. So I'll copy 4, 0, 0, 0, 5, 0. -20 minus 0 minus 0. Notice again, because that first row isn't IJK, your answer is not going to be a vector. Your answer is going to be a number, like the answer to a dot product should be. 2 be my other set of diagonals. That'd be 0, 0, 0. So I add those up, that'd be zeros. I love when there are zeros in my matrix. I'm guaranteed to have some easy things. And so my triple scalar product is 20. If you're curious and you want to try it out, you could go through and do the cross product for B and W, get a vector, and then do a dot product for that answer and U, and it will be the same thing. This is cutting out that middle step. Any questions? There are some uses for triple scalar product. Okay, we're not necessarily going to get into those. Like we're just kind of like nitpicking different things from the chapter 11. We are going to use the cross product to find the area of a parallelogram. Okay, so we are going to use that geometric property. But for triple scalar product, you really just need to be able to perform the operation and get the number value. So our homework assignment is page 793, numbers 5 through 43 odds, and then 53 and 55. You can go ahead and pull out your textbook and get started. We've got about a little over 10 minutes. And I'd be happy to answer any questions that you might have. You may use the restroom.